Hello students, I am Sachitrakar. Welcome to Cars Physics. In this lecture we will start a new chapter, that is circular motion. Okay, circular motion. So we will start from zero. Means from zero concept, from basic concept. We will understand what is circular motion, how many types of circular motion, and what are different terms to explain circular motion. Thereafter, application of circular motion. Okay, and we will solve the numericals using those formula comes in this chapter, both fundamental numerical and application numerical. Okay, then circular motion. See, previously we have completed projectile motion. Projectile motion is two-dimensional motion. Of course, circular motion is two-dimensional motion or motion on a plane. Motion on a plane or two-dimensional motion, just observe. This is x-axis and this is y-axis. Here coordinates are 0, 0. Let a particle starts from this point and moves in a circle. The particle starts from origin where coordinates are 0, 0 and completes a circular path. Completes a circular path. Okay. Let's consider the particle is moving in clockwise order. See, here coordinates are 0, 0. When the particle reaches at this point, let's consider coordinates are x1, y1. Means this distance is x1, this distance is y1. Then what we observe? When the particle moves from origin and reaches at this point, value of x is increasing and value of y is also increasing. When the particle completes a quarter circular path, means here angle is 90 degree, here coordinates are x2, y2. So, till the particle reaches at this point, means completes one quarter of circular path, value of x is increasing up to this value. This is x2 and this value is y2. So value of x is increasing, value of y is increasing. Okay. So see, x coordinate is changing as well as y coordinate is changing. So this is motion on a plane. So here motion on xy plane. Okay. So thereafter, suppose at this point, this is x3. This is y3. Means this distance is x3 and this distance is y3 along y-axis. Means value of y is decreasing but value of x goes on increasing till the particle completes a semicircular path. Here x4, y4. Here y4 obviously is 0. Value means distance along x-axis is x4 but distance along y-axis is 0. Okay. And the particle continues to its motion till it reaches at this position, value of x and y increasing, thereafter decreases, thereafter again value of x decreases. Suppose at this point, you consider this point. To reach at this point, distance along x-axis let x5 and distance in y-axis is y5. Means value of x is decreasing, value of y is increasing. In this direction, value of y is increasing but value of x is decreasing. And here again, the values are x2, y2. Okay, without considering direction, positive, negative. Okay, this is x2, y2. Means again, value of x is decreased from this value x4 to x2, but value of y is increasing from 0 to y2. And so on till it reaches the original position. So both values means distances along x-axis and y-axis are changing. Distance along x-axis and y-axis changing. So this is motion on a plane or two-dimensional motion. Okay. So this is about circular motion, how it moves on a plane or how it is a two-dimensional motion, then fundamental definition. So in simplest way, we may say if a particle moves in a circular path, then it is circular motion. Okay, let's see. Suppose a particle is moving in a circle. This is center of the circle, O, and this is radius of the circle, R. Okay. So what is circular motion? Circular motion is the type of motion in which distance of a particle remains same from a fixed point. So, circular motion, or you may complete the definition, a particle is said to be in circular motion if distance of the particle remains same from a fixed point. A particle is said to be in circular motion if distance of the particle remains same from a fixed point. Then what is fixed point? Center is fixed point. If a particle moves in a circular track, then center is fixed. So when the particle reaches at this point, then distance from center is R. And when the particle reaches at this point, again distance is R. When particle reaches at this point, distance is R, and so on. Here also distance is R. So wherever the particle in circular track, but distance from center means distance from fixed point is always same, means equals to radius of the circle. Okay. So circular motion is the type of motion in which a particle moves in such a way that its distance from a fixed position always remains same or always remains constant. Okay. So this is fundamental definition of circular motion. Then what are different types of circular motion? What are different types of circular motion? Circular motion is usually divided into two types. Number one, uniform circular motion. Uniform means constant. So circular motion but uniform. So what remains constant? See, suppose a particle is moving in a circular path with a speed v. Here v is constant, means speed is constant. Thus what is uniform circular motion? The type of this is the type of circular motion in which speed remains constant. So if a particle moves in a circular path in such a way that its speed always remains constant, the particle moves with constant speed, then it is uniform circular motion. Okay? But what changes? Speed remains constant. But what changes? See, speed has only magnitude. If magnitude is constant, then speed is constant. But velocity is a vector quantity. Okay? It has a direction. As we have discussed in kinematics, thus just one says to define velocity in terms of speed, then simply we may say speed in a given direction is called as velocity. Means speed is magnitude of velocity. So here magnitude of velocity is constant. But what about direction? See, particle is moving in anti-clockwise order. When the particle is at this point, then direction of velocity is determined by drawing a tangent. You know it. If a particle moves in a curved path, the direction of velocity at any instant, at any position can be determined by drawing a tangent. Since the particle is moving in anti-clockwise order, here direction of velocity is along the tangent. And at this position, direction of velocity is along the tangent. At this position, direction of velocity is along the tangent, and so on. See, in this type of circular motion, speed remains constant, but velocity doesn't remain constant. Velocity doesn't remain constant. What? Magnitude of velocity remains same. Velocity changes. Due to only change in direction. Velocity changes due to only change in direction, because magnitude of velocity, that is speed, is constant. So you may observe that velocity is a vector quantity. A vector changes due to only change in magnitude, or due to only change in direction, or due to change in both. Okay. Thus velocity may change due to only change in speed, or due to only change in direction, or due to change in both. Here velocity changes due to only change in direction. So this direction. So you may take number of tangents are not same. So V1 not equals to V2, not equals to V3. So velocities are different due to different directions, but we may say magnitude of V1 is equal to magnitude of V2 is equal to magnitude of V3, that is equals to V, because speed is constant. Thus in uniform circular motion, speed is constant, means magnitude of velocity remains constant. This is constant, but direction doesn't remain constant, so velocities are different. So in uniform circular motion, velocity changes due to only change in direction. Okay. Then comes number 2. Non-uniform circular motion. It is the type of circular motion in which speed doesn't remain constant. The type of circular motion in which speed doesn't remain constant. Speed doesn't remain constant. Okay. Speed doesn't remain constant, but you see, if a particle moves in curved path, then direction is changing always. Direction always changes, but here speed is not constant. So in non-uniform circular motion, here velocity changes due to change in both magnitude means speed, and direction. So in non-uniform circular motion, velocity changes due to change in both magnitude and direction. So in non-uniform circular motion, speed changes. Speed is not constant. Thus magnitude of velocity changes. Again, direction changes. Direction at any instant is determined by drawing a tangent. So in non-uniform circular motion, velocity changes due to change in both magnitude and direction. Okay, so this is about type of circular motion. Two types of circular motion: uniform circular motion and non-uniform circular motion. Is it clear? Is it clear to all? Okay, fine. Then in circular motion, means if we study circular motion, then we have to learn different terminology. What are different terminology? We will learn in this class some terminology. Okay. So first term is angular displacement. Angular displacement. See, angular, the term comes from angle. The term comes from angle. So angular displacement, we know displacement means we know linear displacement. Okay, the shortest path from initial to final position is linear displacement. So here angular displacement. So displacement is vector. Means here we do consider angle as a vector quantity. Here we do consider angle as a vector quantity. So it is called as angular displacement. Okay. Suppose particle is in circular motion. I do consider here the particle is moving in anticlockwise order. This is center of the circle. This is radius of the circle. Okay. Let initially at t is equal to 0, the particle is at a when instantaneous time is 0. Okay. The particle goes on moving along the circular path. Okay. Let at any instant the particle is at B. Okay. Here R is radius. Initial position of the particle is A. So the position of A with respect to center is shown by a radius vector or radius vector, or you may say R is position vector of A with respect to center O. R is position vector of A with respect to center. So R is also treated as a position vector which shows position of the particle with respect to center. Okay. So R is radius vector. So when the particle moves from A to B, see, this radius vector sweeps an angle. This radius vector sweeps an angle about the center. Now this is direction of position vector. This is initial direction of position vector O to A, and this is final position when the particle reaches at B. Let's consider this is initial position, this is final position, and position vector is directed from O to B. And this position vector sweeps an angle about the center. Okay, so theta, angular displacement theta, is treated as a vector quantity. It is angular displacement as we say. Okay, then what is theta? C, A to B. Let this is S, linear distance. Okay. If you consider this angle is very small, if you consider angle subtended at the center is very small, then A to B is a straight line. AB is a straight line because the circular path is sum of a number of straight lines. Okay. So we may consider A to B is a straight line. So this is linear displacement. If you consider like this, then angle about the center theta will be very small. If AB is treated as a straight line, then angle about the center subtended by position vector is very small. Okay. Okay, means here consideration is there. If AC is very small, means AB, distance AB is very small, then theta tends to 0. Means very small. Theta is very, very small. If arc, AB is arc. If arc length is treated as a straight line, means very small, then theta tends to 0, means theta is very, very small. In this case, angle is treated as a vector quantity. Okay. So, what is angular displacement? You see, as you know, angle is equal to arc length divided by radius. Arc length divided by radius. So here, angle is theta, arc length is s, and radius is r. So theta is equal to s by r, or you may say s is equal to r theta. See, we'll learn how to determine direction of angular velocity. So direction, not velocity, angular displacement, direction of angular displacement is determined by right hand thumb rule. Direction of angular displacement is determined by right hand thumb rule. See, the particle has moved from A to B. Okay. Then how can you determine direction of angular displacement? Put your fingers along the direction of position vector, fingers of right hand thumb rule. Put your fingers along the direction of position vector, means initial position is A. Now position vector sweeps an angle theta about the center. The particle has moved in anticlockwise order. Thus curl your fingers in anticlockwise order. Then erect thumb represents direction of angular displacement. If the particle is moving in anticlockwise order, then direction of angular displacement is outward. And obviously, if the particle moves in clockwise order, that initially the particle is at A and moves to position B in clockwise order, this is R, OA, OB, this angle is theta. Then, if the particle moves in clockwise order, curl your fingers from A to B, then direction is inwards. See, suppose this circle, means plane of this circle is parallel to this plane, means parallel to whiteboard, plane of whiteboard. Suppose a circle is drawn which is perpendicular to whiteboard, like this. Perpendicular to whiteboard, means circular path is on this plane, perpendicular to whiteboard. So if the particle is moving in anticlockwise order, this is it, this is B, this is OA, this is OB, and there is theta. Then what is direction of theta? Curl your fingers in anticlockwise order on this plane. On this plane, circle is on this plane. Then from A to B, curl your finger in anticlockwise order, then direction is upward. See, here direction is outward on this plane, means perpendicular to this plane, and here also angular displacement is perpendicular to plane of this circle, means in upward direction. This is direction of angular displacement. If the particle moves in clockwise order, this is A, this is B, this is theta, this is R, this is R, this is O. Then in clockwise order, just imagine, if a particle moves in clockwise order on this plane, if the particle moves in clockwise order, then direction is downward. And here, if the particle moves in clockwise order, then direction is inwards, and here direction is downward. So this is direction of angular displacement. So whatever may be, here outward for anticlockwise motion, outward for clockwise, inward, and here for anticlockwise order, upward or clockwise motion downward, whatever way. The direction of angular displacement is perpendicular to the plane of revolution. Direction of angular displacement is perpendicular to the plane of revolution. Okay, it may be outward, may be upward, may be inward, or may be downward, whatever. Direction is perpendicular to plane of the revolution of a particle. Is it clear? Okay. So direction of angular displacement, direction is along the axis. This is axis. What is axis? Axis of a circle which passes through center of the circle and perpendicular to the plane of circle. Or anti-clockwise order, this is axis. Outward. Axis is passing through center and perpendicular to plane of circle. Perpendicular to plane of circle. This is a circle. This is plane of circle and this is axis of circle. This is axis of circle. The axis is passing through center and perpendicular to plane of circle. Perpendicular to plane of circle. Okay. So direction of angular displacement is along the axis. So we may write angular displacement is on axial vector. So as we have discussed, you know it, if a vector is directed along the axis, then the vector is called as axial vector. So angular displacement is axial vector. Is it clear? See, this is direction of linear displacement. If you consider AB is a straight line, this is direction of displacement. But direction of angular displacement is along the axis. Okay, this is direction of linear displacement. This is direction of angular displacement, which are perpendicular to each other. So this relation, both the relation, this relation or these relations are applicable only for magnitude. Then this is not in vector form. This is not in vector form. We can't write. S vector is equal to R vector theta, or S vector is equal to R into theta vector. We can't write. This is wrong. You get direction of position vector, direction of position vector and direction of linear displacement are perpendicular. Again, direction of angular displacement and direction of linear displacement are perpendicular. So we can't write this. So these relations are only applicable for magnitude. Magnitude of linear displacement can be calculated by taking product of magnitude of position vector and theta, means magnitude of angular displacement. So theta here, what is unit of theta? See, theta is a plane angle, here motion on a plane. So unit of theta, you know, unit is radian, unit of plane angle is radian, and dimensional formula of angle, this is arc length. Arc is length, radius is also length. So length by length means no dimension, mg, lg, d. So angle is such a physical quantity. Angle is such a physical quantity which has unit but no dimensions. Okay. Length by length. So ratio of two same physical quantities, arc length and radius length. So ratio of two same physical quantities, thus dimensions is 0. Okay. So this is about angular displacement. Okay. Then second term, angular. Okay, just take some fundamental points. Number 2 term, time period. t. See, particle moves in a circle. Suppose in anticlockwise order, the particle starts from A, radius is r. The particle starts from A when time is 0. So starts from A and completes one revolution and again reaches at A. Time taken by the particle is t. So what is time period? It is time taken for one complete revolution. For one complete revolution, time taken for one complete revolution means time taken from 0 to t. So time taken is t. T is time period. So obviously unit of time period is second. Unit of time is second. Then next term, frequency. F. So what is frequency? Just reciprocal, you know it. It is number of revolutions in unit time. So this is the time taken for one complete revolution, but frequency is the number of revolutions per unit time. So F is frequency, means F revolutions per 1 second. Unit time means we do take in SI second, in 1 second. Then for one revolution, F revolution is made in 1 second. Right, like this, F revolution is made in 1 second or unit time. For one revolution, time is 1 by F. But for one revolution, time is time period t. Thus you may write time is equal to reciprocal of frequency. So unit of frequency is equal to, in accordance with this formula, frequency is equal to reciprocal of time period. So unit of frequency 1 by time means second inverse, or you may write it hertz. Second inverse or hertz. So dimensional formula t to the power minus 1. Okay. So this is time period and frequency. Next. Very important in this lecture. Very important. Number 4, angular velocity, omega. See, the particle is moving in a circle in anti-clockwise order. Let the particle, this is position vector, this is center, let the particle move from A to B. A to B. So this angle is theta. Theta is angular displacement. Is it clear? Then you know linear velocity. Linear velocity in kinematics, motion in a straight line. So linear velocity is a rate of change of linear displacement. Linear velocity is defined as rate of change of linear displacement, and in similar way, we may say it is rate of change of it is rate of change of angular displacement. Linear velocity is rate of change of linear displacement. Angular velocity is rate of change of angular displacement. You see, suppose you do need average angular velocity. Average angular velocity, then it is the ratio total change in angular displacement to total change in time. So theta 1 is angular displacement when time is t1. Theta 2 is angular displacement when time is t2. Just you take some examples of angular displacement. Let the particle starts its motion from A and reaches at B. Okay. Starts its motion from A and reaches at B. Let angle made at the center is theta 1. Then from A to B, angular displacement is equal to theta 1. Okay. Let now the particle again moved from B to C. This is C. Okay. This total angle is theta. Then from B to C, angular displacement is equal to, see, this total angle is theta 2, this angle is theta 1, so from B to C this angle is angular displacement, means it is equals to theta 2 minus theta 1, theta 2 minus theta 1. Okay, so angular let the particle is at position B when time is t1, the particle at position C when time is t2, and here time is 0. At A time is 0, when the particle is at B time is t1, when the particle is at C time is t2, means when angular displacement theta 1 time is t1, when angular displacement is theta 2 then time is t2. Then resulting angular displacement is theta 2 minus theta 1. So average angular velocity is total change in angular displacement to total change in time. So in similar way, instantaneous angular displacement, you know this linear velocity, instantaneous angular velocity, you know instantaneous linear velocity, this is instantaneous angular velocity. So to calculate instantaneous velocity, we have to assume this may be written as delta theta by delta t. Okay, total change in angular displacement divided by total change in time. So for instantaneous angular velocity, the interval of time is very small. At any instant, interval of time tends to 0, and delta theta 1, delta t is equal to d theta by dt. Okay, this is for instantaneous angular velocity. Then what is unit of angular velocity? Angle upon time. This is angle, this is time. Angle is radian, plane angle. Time is second, radian per second. And dimensional formula of angular velocity, radian has no dimensions. Then 1 by time, m to the power 0, L to the power 0, t to the power minus 1. Okay. So angular velocity is also called as angular frequency. Angular velocity is also called as angular frequency. Sometimes students you are getting confused. So frequency, we have already studied frequency, but unit of frequency is hertz, second inverse. But unit of angular frequency is radian per second. This is the difference. So sometimes in numericals it is written frequency of a body is radian per second. Then you have to understand that this is angular velocity or angular frequency. Okay, not like this is also the way. In some numericals it is mentioned that the body is moving with angular velocity of 10 radian per second, then it is correct. This is angular velocity. But if it is mentioned in revolution per second, then it is frequency. Okay. Then how to get frequency? We'll see it. Okay. This is unit and dimensions. Then what is direction of angular displacement? Direction of angular velocity. Again, direction of angular velocity is determined by right hand thumb rule. Direction of angular velocity is determined by right hand thumb rule. Okay. Change in angular displacement means direction of delta theta is equal to direction of omega. Okay. Then if the particle is moving in anticlockwise order, then angular velocity is in outward direction. If you take plane of circle like this, then angular velocity is in upward direction. upward direction. Okay, and accordingly, if a particle moves in clockwise order, direction of angular velocity is inwards, or in this case, for clockwise order, direction is downward. Whatever may be, angular velocity is an axial vector. Angular displacement is axial vector. Angular velocity is also axial vector. Okay. Let's relate now. Angular velocity. See, suppose a particle completes one revolution. A particle completes one revolution. The particle starts from it when time is 0, moves and completes one revolution, again reaches at it, and time is t. Then angular displacement, total angular displacement for one complete revolution is 2 pi. Then magnitude of angular velocity is, total angle is 2 pi, total time is t. Total angle subtended at the center for one complete revolution is 2 pi, total time is t. Okay. Again, you know 1 by time period, reciprocal of time period is frequency. So angular velocity may be written as 2 pi into frequency. Okay. Then relation. Okay. We know theta. Angular displacement is s by r. And angular velocity, see, instantaneous angular velocity, I am taking magnitude of angular velocity is d theta by dt, means angular velocity, magnitude of angular velocity is d by dt of theta. Theta is equal to s by r. Okay. Then r is constant, radius is constant, then omega is equal to 1 by r into ds by dt. Okay. The linear motion is along the circular path, as we have discussed. Okay. So this is linear velocity, means magnitude of linear velocity ds by dt. So we may write omega is equal to ds by dt is magnitude of linear velocity v by r. ds by dt is v into 1 by r, means v by r. So finally we may write v is equal to r. So here, if the particle is moving in anticlockwise order, then velocity is v. We are considering now uniform circular motion, then direction of velocity is along the tangent. This is direction of position vector. Okay. Then this is also direction of position vector. Then angle between position vector and velocity is 90 degree, means here position vector and linear velocity, direction of linear velocity are mutually perpendicular. Also, direction of angular velocity is also perpendicular to both position vector and linear velocity. Angular velocity is along the axis t. These two, position vector and linear velocity, are on this plane, but angular velocity is perpendicular to the plane. Thus, you may conclude direction of linear velocity, direction of position vector and direction of angular velocity are mutually perpendicular to each other. If this is along x-axis, this is along y-axis, and angular velocity is along z-axis. So they are mutually perpendicular to each other. So finally you may write v is equal to r omega. So it is in scalar form. It is in scalar form, means only for magnitude. We can't take it in vector form. See, if you write v is equal to position vector into omega, or v is equal to r into omega vector, then this is wrong. Because direction of position vector is not as that of direction of linear velocity, and direction of angular velocity is not same as that of linear velocity. They are perpendicular to each other. So in vector form it will be wrong, but it is correct in scalar form. So this relation is used to calculate only magnitude. Another thing, see, in circular motion, This is very important to know. In circular motion, V is perpendicular to R only. Only in circular motion V is perpendicular to R. So thus in only circular motion you may write omega is equal to V by R, or magnitude of angular velocity is equal to V by R. This is true only in circular motion, but not in all types of motion. Angular velocity doesn't come only in circular motion. Okay. Means distance of the particle from the center is constant in circular motion. This may not happen in all types of cases. We will see those cases. Okay. So this is only for magnitude. This much. Then we will go to some discussion analysis. Okay. Angular velocity. Angular velocity means particle is moving in a circle and angle is subtended at the center, means position of the particle is changing along the circle and angle is changing. This is the concept. So as we have discussed in kinematics, position of a particle depends upon the position of observer and frame of reference of the observer. Okay. Position of a particle is determined by position of observer, means state of observer and frame of reference. So this is a conceptual point. Angular velocity depends on position of observer. Okay, let's see a question. Suppose a particle is moving in a circle in anticlockwise order. This is center. Suppose the particle starts its motion from A in anticlockwise order. Is it clear? The particle starts its motion from A in anticlockwise order. The motion of the particle is observed by two observers. One of observer is at center and another observer is at diametrically opposite point. One of the observer is at center and another observer is at diametrically opposite point. When instantaneous time is 0, the particle is at A, and the motion of the particle in anticlockwise order is observed by two observers O and OS. Let the particle moves to position B. Okay. Time taken by the particle to reach at B is T. This is radius or position vector. Okay. And angle subtended here is theta. Then angular velocity as observed by O, which is at center, is equal to total angle is theta as he observes. Total angle is theta and total time is T. Is it clear? But O dash, the observer at O dash, see, for O dash the total path means O dash to A is position vector. So R is position vector with respect to center, and R dash, R is O and R dash is O dash is position vector with respect to OS. With respect to OS, then as observed by OS, angular velocity, magnitude of angular velocity, of course, as observed by OS. See, OS observed, the particle moves from A to B, means the position vector changed from position A to position B. Then angle subtended about O dash, let alpha. The angular velocity as observed by O dash is total angle subtended is alpha and total time again T, 0 to T. Then what is the relation between theta and alpha? As you know, theta is equal to 2 alpha. Theta is angle subtended at center and alpha is angle subtended diametrically opposite points. So theta is equal to 2 alpha. So you may say angular velocity observed by O is 2 alpha by t. 2 alpha by t. Then we may say magnitude of angular velocity observed by O is equal to twice alpha by t, means angular velocity observed by O dash. So magnitude of angular velocity depends on the position of observer. If there are two different positions of the observer, then angular velocity or angular displacement observed by the observers are different. This is the concept. Okay, fine. The next point. Okay, as we have discussed, only in circular motion angular velocity is equal to v by r for circular motion. So as we have discussed, only in circular motion, see, this is direction of position vector, or this is the direction of position vector, this is the direction of velocity, so angle is 90. So only in circular motion v and position vector, linear velocity and position vector are perpendicular. This doesn't happen in all cases as we have discussed. Okay. Let's consider this is a straight truck. This is a straight truck. Okay. And this is position of a vehicle. Position of a vehicle. Okay. This vehicle is initially at point A. At point A. Initially at point A. And it moves along the straight track with a constant velocity, let 20 meter per second. This is constant. It moves with a constant speed along a straight line with a speed of 20 meter per second. Okay. The motion of this vehicle is observed by two observers. This observer is O dash. Okay. Let distance of A from O dash is 30 meter. Okay. And another observer is observing the motion of the vehicle remaining at O. Again, O dash A is 30 meter and O dash A is 30 meter. Again, OA is also 30 meter. This is 30 meter. This is also 30 meter. Okay. So the vehicle moves in a straight line. So what observer O dash observes? Observer O dash observes that the vehicle has only a linear velocity. The vehicle has only linear velocity or only linear speed, that is 20 meter per second. But for O dash, let now the vehicle reaches at this position. Now the vehicle reaches at this position. Now the vehicle reaches at this position and this position is let B. This position is B. Okay. Let the vehicle has travelled a distance of 40 meter from A to B. Is it clear? For observer O dash, the body has covered a distance of 40 meters with a speed 20 meter per second, linear speed 20 meter per second along a straight line. But for observer O dash, he observes that the vehicle is moving along a straight line, but you see, this is interesting. Suppose a particle is initially at A, position vector is O, and particle moves to position B. Okay. Then angle subtended at the center is theta, which is angular displacement. So angular displacement also in anticlockwise order. Okay. You are observing that initially position is at A and it moves to position B. Initially, the particle is at A. This is the tip. Tip is particle A. Initially, the particle is at A. It is moving to B. Okay. Or you may see a particle is at B. Initially at B and moves to A. Then angle is let again theta. Then you are observing that the particle is initially at B. This is position B and moves to A. Moves to A. Means to observe angular displacement, you have to turn your head. For anticlockwise motion, turn your head. If the circular track is on this plane and you are observing from outside of this plane, okay, then for anticlockwise motion you have to turn your head, and for clockwise motion you have to turn your head. Okay, suppose this is a particle just in front of me. This particle is moving forward. This is the radius vector, then radius vector will go on changing its direction. Then angle is subtended theta about this line, theta. Then this body is moving in forward direction. Then this is angular displacement. If the body moves in this direction, then this is angular displacement. So we have to turn the head either towards left or towards right. This is initial position, towards left or towards right. See, O dash has not to rotate his head. O dash has not to rotate its head because the body is moving in a straight line with respect to O dash, but with respect to O. The vehicle is reached that point B. Okay, then O is observing. The body is at A or the vehicle is at A and moves to B. Moves to B. Then I am rotating my head left to, I am the observer O. I am rotating my head towards right. Towards right. Then angle subtended about observer O is theta. Obviously this angle is 90 degrees. Then bring this triangle outside. Along this direction, vehicle is moving, velocity is v, linear velocity. This is the initial position A. Distance from O is 30 meter. This angle is 90 degree, and finally it reaches at B. It is 40 meter. So if this angle is 90, obviously 90. This is 30, this is 40, then this is 50 meter. Okay, and this angle is let theta, angular displacement about O. Then what is value of theta? Then tan theta is equal to perpendicular upon base 40 meter divided by 40 meter divided by 30 meter. That's equals to tan theta is equal to 4 by 3. If tan theta is 4 by 3, then you know theta is equal to 53 degree. Theta is equal to 53 degree. See, this angle is 90, this angle is 53. So this angle will be no doubt 37 degree because 53 plus 37 is 90. 90 plus 90 is total angle is 180. Okay. So in this case, see, this was position vector R 30 meter, and for position B, this is position vector R2 50 meter. But in this case, this velocity is not perpendicular to direction of position vector. This is direction of velocity. This is direction of. If you produce this, means parallel shifting. This 50 meter. This is also position vector, and angle between velocity and position vector is not 90 degree. Not 90 degree. This is some other angle. Then what? How can you get perpendicular component? As we have seen, this is only true in circular motion, because in circular motion velocity and position vector are perpendicular. So for other cases, except circular motion, except circular, other cases, omega is equal to v. Here velocity is perpendicular, but here velocity is not perpendicular, so we have to take perpendicular component of velocity divided by magnitude of position vector. Okay, magnitude of position vector. Okay, then this is direction of velocity, this is direction of position vector. Draw a line perpendicular. This angle is 90 degree. So obviously this angle is 90 degree. No doubt this angle is 90 degree. Then this is component of velocity perpendicular to position vector. Then this is perpendicular component. Perpendicular component of velocity. Then we have to get this. What is V perpendicular? Means perpendicular to position vector. See, if this angle is 37, this angle is equal to this angle, opposite angle, so this angle is 37. But total angle is 90, so this angle is 53 degree. This angle is 53 degree. This is direction of velocity. So component of velocity along this direction means V perpendicular is equal to V cos 53. This is V cos 53. Okay. This is the result. This angle is 53, this angle is 33, and this is V sin 53. But perpendicular component is V cos 53, and that's equals to V. V is 20 meter per second. This is constant into cos 53. Just make a triangle. O, A, B. This angle is theta. This angle is 90. This is 30 meter. This is 40 meter, and this is 50 meter. Is it clear? Then tan theta is equal to 40 by 30, perpendicular upon base, and cos theta is equal to base upon hypotenuse. This is hypotenuse, this is base, means 3 by 5, 30 by 50, or 3 by 5. Okay. Then this comes 20 into 3, 60, divided by 5, that is 12 meter per second. 12 meter per second. You see, in this way also, if you are in doubt, then see in this way. This is 53. This is 53. This angle is 90 degree. This is 40 meters. This is 30 meters. This is 50 meters. This angle is theta. Then cos theta. Base upon hypotenuse 30 by 50. Is it clear? Now it is clear. Okay. Then V cos 53. Cos 53 is 30 by 50. 30 by 50. V is 20. 3 by 5 into 20. 20 into 3, 60. 60 by 5. That is equals to 12 meter per second. Okay. Then now, what is value of omega? Can I erase this part now? Then omega is equal to V perpendicular divided by R. Here R is 50 meter. Magnitude of position vector to position V is 50 meter. Then here magnitude of angular velocity is perpendicular component is 12. And this is 12 by 50 or 6 by 25. 6 by 25 radian per second. Okay. 60 by 5, 12, 12 by 50, 6 by 25 radian per second. This is 53, this is 37. So this angle is opposite angle is 37, this angle is 53. So this is V cos 60, cos 53, this is V sin 53. We need perpendicular component to radius or position vector. Then omega is equal to V perpendicular divided by radius or position magnitude of position vector. V perpendicular is V cos 53. Cos 53 is 30 divided by 50. Then 60 by 5, 12 meter per second. and perpendicular component is 12 divided by radius is position vector is 50, then 6 by 12 by 50, 6 by 25 radian per second. Is it clear? Okay. Then what is angular velocity in vector form? Just see. Suppose particle is moving in anticlockwise with uniform speed, uniform circular motion. This is position vector. This is position vector. This is direction of velocity, and this is direction of angular velocity along the axis. As you know, in scalar form we have written v is equal to r omega. Then in vector form you may write v is equal to omega vector cross r. See, direction of omega is perpendicular to plane, in this case outward. This is direction of omega, and this is direction of r. This is direction of omega. Okay, I will call these fingers omega cross r. Keep your fingers of right hand along the direction of omega. Omega is outward, here this is outward, and this is direction of r. Omega cross r. Omega cross r is tangential. Omega cross r is v. Okay, and angle between them is 90 degree. Okay, this is in vector form. Vector form of linear velocity. V is equal to omega cross r. Omega is angular velocity. Okay. Then another case you may see in projectile motion. We have completed projectile. So I am giving you example of projectile motion, two-dimensional motion. Let a particle is fired from this position with initial velocity u, making an angle theta with horizontal at t is equal to 0, and particle finally strikes the ground at this position. This position is A, this position is B. And as you know, if air resistance is neglected, then velocity of projection is equal to velocity of striking. This is also angle of projection. Angle of projection is equal to angle of striking. This angle is theta. Okay. Then it is asked, calculate angular velocity when the particle strikes the ground or horizontal surface strikes the ground. See, particle starts its motion from A and strikes on the ground at B. Then we have to calculate what is angular velocity of the particle when it strikes the ground with respect to position O, or with respect to A, with respect to C. This is final position with respect to A. So means this is AB is position vector. AB is position vector. This angle is theta. AB is position vector with respect to A. AB is position vector, but you know this position vector is range. Here magnitude of position vector is range. Is it clear? Is it clear? Okay. Then angular velocity. What is angular velocity? Perpendicular component of velocity, V perpendicular, divided by magnitude of position vector, C. This is direction of position vector. This is velocity of striking. So this component is u cos theta, same as that of in this case u cos theta. Horizontal component always remains constant, and this is u sin theta. Since theta is same, u is same, so vertical component is also u sin theta. So this is V perpendicular because this angle is 90 degree. As you produce this position vector, this angle is also 90 degree. Then what is magnitude of angular velocity? Perpendicular component of velocity is u sin theta. U sin theta divided by range, where you know range is equal to u square sine 2 theta divided by g. Then putting the respective values, we can calculate magnitude of angular velocity. Okay. So this is about introduction to circular motion, means two-dimensional motion, circular motion. This is only introduction to circular motion. Okay. Next lecture we will again meet with some beautiful concepts. Thanks, my children.